which is, again, that's not what you expect to happen. All of the academic literature is like, your students are all tactile learners and want to play with Play-Doh in class. There's no possible way to understand key value pairs without using your hands. Um, which I do not believe, but we'll find out today because I'm about to teach you about key value pairs without using your hands, and so you'll either understand it or not, and then we'll have a data point. Um, uh, we are in the part of the class where I sort of ran out of things that do not intersect with any previous class I've taught. So we have to do a quick, I don't know, digression through some potentially redundant content for some of you and not others. Of the remaining 8 lectures, 5 of them are adapted from other classes. None of you have taken all 5 of these classes. Yeah, they're from distinct classes, right? So as you all know, the design objective of this course was to Voltron together sort of a large number of learning objectives from a variety of different courses. And so essentially what's going on is, of the 8 remaining lectures, most of them are 2 lectures run at double speed from different classes. So there's, for example, a Bitcoin lecture. Today's Malloc lecture is actually 1 week of content from the 5th week of CS 271 last year. I decided, and I was going to do this, I was going to remake the graphics in GraphViz so that the graphics are open source, and I looked at how cute the old graphics are, and I hadn't even changed the graphics. So these are still the plagiarized graphics from UIUC. Okay. Welcome to CS 276, and maybe CS 540. We learned about anti-patterns last time, and one of the anti-patterns we learned about was length prefixed vectors. That's a terrible way to do, well, it's not that terrible. It's, there's reasons not to do it that way. In theory, you finished big RSA shortly before I started talking, and in theory, you will begin list T shortly after I'm done talking. What is big RSA, like, super hard? My ability to evaluate difficulty completely went away because I found out I was evaluating myself sometimes when I was sleep deprived and sometimes when I was not. So I was actually just measuring how tired I was, not how hard things are. Big RSA is hard. Wow, okay. So like, again, I did it over break when I was well rested and I was like, this is the easiest assignment so far. Okay. Does anyone have any questions about big RSAs or anything we should talk about? I can just live code right now. Wait, didn't I gave you the solutions, right? Did I not do that? I did that. Yeah. No, that's not it. It's not public. I wasn't gonna give the solutions, then I realized the directory was named ref RSA, which is 6 characters, so I published it. Um anyways, you can verify that this thing is working, probably. Is there some way to run workflows? Right, okay, so this is gonna run. What's it gonna run? Well, we can look. It is going to make check, okay? What's make check gonna do? Let's go into our make file. One of the best types of files, if you ask me. Okay, so there's a bunch of defines up here. These are variables, right? Okay, let's check. It's gonna big RSA and big key. Okay, so big RSA is going to compile big RSA.c with my big num library, which is currently set to be big GMP. What's big GMP? This is a partial solution I provided to you. This is the solution to 496T implemented with the big GMP library. Yeah. So if your 496T does not work, this does work. Okay. All right, so let's go back to the make file. Okay, so we have bigkey.c, big num, which is big GMP, but you can use your 496T if you want as well. We're going to use our C flags, so all of these. We're going to create something called big RSA and big key, and then we're going to use our C libs. Okay, let's look at the assignment description. What's this say? Okay, right. So blah, blah, blah primes, big GCC, big key. So we're building up to big key. Basically, we need to write this type of output. No problem. Okay. Right. Okay, so we do key generation and encryption. as big RSA and big key. So we're going to make both of those, then we're going to run big key. That's going to generate the keys. I'm going to create a string that's a multiple of 4 characters, which probably means that I thought it was easier to encrypt things that are multiples of 4 characters, right? Why is that? Because things that are multiples of 4 characters are multiples of 32 bits, which means they fit evenly in a word, which means they fit evenly in a uint32t. And so, presumably, my big key, or my big RSA, one of the two, is reading 32-bit words. Wow, there's a lot of code in here. There's 146 lines. Oh, most of it's file I/O. This stuff's boring. Okay. Right, so I'm gonna scan a line. The line is line length. Oh yeah, this doesn't look bad at all. So the 32 bits are to avoid thinking about endianness. Probably. Okay, that's a multiple of 4 characters. Probably. We'll check in a sec. Okay. Then we encrypt and decrypt, and then we check to see if the decrypted is the same as the encrypted. If these two things are the same, the diff returns has a return code of 0, which is represented by this green check mark here. And we can step through, run make check. Boom. GCC does the double compile, key generation, creates the file, encrypts, decrypts, checks the difference. This is a check mark, which means that returned 0. Okay. Oh, that already has quotes on it. Yeah, it's a multiple 4. Okay. Anyways, if you're stuck at any point, you can look at what I did, I guess. I don't know that you should trust me, but I did in fact get big GCD to work. And I did it in a mere... Hold on. This thing's like only like 60 lines, right? I don't know. Like it's like a 200 level class. It seems reasonable to ask you to write a 60-line function, right? I didn't ask for a 200-line function. And separately, this is a version of a probably 20-line function you've already written, right? And this one's also iterative. I don't know if you all preferred recursion on the extended Euclidean algorithm, but this is way easier recursively. It's just slower. And it doesn't have to be slower. It's just likely to be slower. But like a lot of these things are just wrappers, right? Okay, so that's the tour of ref RSA, which presumably giving you this code helps much more than any combination of words I could say. With that caveat, are there any words anyone would like me to say about anything? Discombobulate. Okay.
Blimp.
That's an all-timer. Blimp. Yeah. Just one of the greats. We don't want to pit the greats against each other, but like I would pit Blimp against anyone, right? They've got a submarine sandwich brand named after them. That's so elite, right? The only other word that powerful is Quizno. Now we all know that the C programming language is perfect and contains no design decisions that could be improved. But if it did, one of those might be the data clump anti-pattern, which is here. And we talked about this last time for 90 minutes, so you all know what this is. Let's solve this problem today, and we're going to solve it using malloc and free. The more complete way to solve this is with struct, which we're going to do on Tuesday. We don't have this class on Monday, right? We use something else on Monday. It's possible I've been coming here and lecturing to an empty room every Monday and just have no memories of it, right? If you all seem confused, maybe you're getting exactly 2/3 of lectures. So we all know Python here, right? Yes, indeed. And Python has no arrays, as we are aware of, right? The basic data types in Python are, integers, strings. They're called floats, right? They're not called doubles or anything. And then NumPy implements arrays, but that's like kind of cheating because really what NumPy does is just expose a bunch of things that are C. So like, yeah, good job, Python. You used a good language. Great, great work. Um, some people, not necessarily me, who are the people who would be annoyed by this? Maybe like theoretic, like language theorists, like someone that did a thesis in like programming languages or compilers or something. They sometimes find it annoying that Python programmers don't know the difference between lists and arrays. Here is one reason this may have felt annoying to you. At various points in this class, I've referred to an array in C as a buffer without introducing that term. I think people older than me mind-controlled me into using that word. And there's actually no reason to use the word buffer, probably, in 2025. Maybe that's wrong. But I think if you've been designing programming languages for 20 years and you've always referred to an n-length collection of bits, which you use as a workspace, as a buffer, right? Then you would probably get really annoyed when you start talking to Python programmers and they don't know what a buffer is. Because you never need to set aside n bits to do anything in Python. You always just create a list and it can be of arbitrary size. You don't have to plan ahead, right? And we could argue that if you don't have to plan ahead, you don't get used to thinking about how much memory your applications use. You write an app for the space station that overloads its hard drive. The space station comes tumbling down over the Indian Ocean, causing an international incident, right? So these things can cost money quickly. My understanding is that internally, and I've never looked at the Python source code, I cannot be bothered. Have any of you looked at the Python source code ever? Right? It looks like a mess. And it's very, very fast. So I cannot disagree with a single thing they do, right? Like the great thing about Java is it was terrible. So it's very you could just be like, wow, this language is slow. And then you're like, you try to do that with Python and you're wrong, right? Everything Python does is fast. It's weird. It's like complaining about a Lamborghini. Which I'm accepting donations of, by the way. If you find a spare Lamborghini, just park it outside my house, which you don't know where that is. So the Python list is built on top of an array. And when lists, which is an abstract data type, something that provides a series of public APIs, basically, like add, remove, index, so on. When you take the idea of a list and you implement that list by taking an array and using that array with a combination of computing operations to implement a list, we call that an array list, and its competing formulation is the linked list. This week, you will be assigned to implement a list, and you will not be assigned to do an array list or a linked list. I do not care. You do not care, probably. The most likely thing is you will pick some way of implementing it, and then either wish you chose the other one, or not have any thoughts at all. Those are the two most common experiences we have. I am a dogmatic linked list enthusiast because of my unrequited love for Alonzo Church's lambda calculus, which is made out of linked lists. And I hope that none of you have that uncommon misfortune. I'm introducing the two terms here, abstract data type, which is the idea of something that we can imagine, like a list, and a data structure, which is the physical allocation of transistors in actual existing program memory. So one of these is physical and one of these is linguistic. We don't want to draw a very firm boundary there because we could in fact design hardware that implements the abstract idea of a list, but we don't. It is easier to use a combination of hardware and software to achieve a list. This is a attempting to emulate an array using a Python array list. Here in C, we have some restrictions. We have to declare the integer type, and then we give the size of the array. What is this doing? You are telling the compiler, you are telling GCC, I need 10 things of size int, that is 10 times most likely 40. So you are getting 40 bytes back. and then you say populate those 40 bytes with these numerical values, right? Now, that is allowed because when we declare variables, we get initial bits on the stack. So we get these bits on the stack, and the stack is a thing we're going to introduce. And when your program is running, it just has access to those 40 bytes. I think I was saying bits and bytes interchangeably. It's 40 bytes or 40 times 8, 320 bits. Now, in the C programming language, if you attempt to later set an array equal to something defined in bracket notation, this draws a compiler error. The reason this draws a compiler error is because this operation, specifically in the C programming language, requires provisioning some amount of memory, and it is ambiguous what those requirements are. This is an incomplete sentence in C, and so we cannot write it, and you can verify this. Now, the next line, is a complete sentence in C. We are completely allowed to request the 15th element of a 10-element array. Nothing is stopping us. Arrays do not maintain their own length. All that is going to do is it is going to calculate where in physical memory, in the array data structure that exists in actual transistors, it is going to count transistors until it gets 15 away from something, and it is going to attempt to write to that location. Sometimes this will be allowed, sometimes it's not. When I ran this, I got an error called stack smashing. The reason for that is because when you declare that array, you take up some space on the abstract data structure known as the stack, which is maintained by the operating system. You write to a portion of the stack that you're not supposed to have access to because you asked for 320 bits and you need 480 bits to write to that location. So when you write to that location, you are writing to a location which you do not have authorization to write to, and the operating system terminates your program.
Then, like line 2, have that be like 0 through 9, would it work?
No, we cannot assign arrays at any time other than initial declaration. I believe C11 might have started allowing you to do this. My recollection of this, which could be wrong, I mostly actually stay away from this personally as a coding style issue, and this is one of the reasons I use the very aggressive tags. I think for a while you were allowed to do that in C99, and then it was taken away in C11 because it was considered so dangerous. So just try it, and try it with your compiler settings. The real reason you shouldn't do that is because the benefits of writing C are that you know what memory you're working with, and it is unclear what memory you're working with there. If you want to do that, you should change languages. We can also do this with other types. I don't know. Other types are boring. That said, this thing, R, it is simply referring to a memory location. It is referring to the memory location of this 0. And so we would think perhaps, oh, can we put something else at a different location? No, we cannot. This character star string is also describing a memory location, but it is giving a memory location we know in our modern devices that is of size 8 bytes. And R3, which is this value here, is that right? No, it's this value. It's 0 indexed. Okay. This value is an integer because it is declared as an integer, which means on my device it is 4 bytes in size. So we get a compiler warning that we're trying to put 8 bits of information in 4 bits of space, for 8 bytes of information in 4 bytes of space. There do exist pieces of physical hardware where that would be perfectly legal. Any device where incidentally the int is the same size of the star, that is completely reasonable. And that was common on 32-bit architectures, which you can still buy. Right? They're slower. They're not used for the things we use them for, which is infinite scroll on Instagram and send email. And they are fine for everything else like drive car and take picture. This is against the law. We don't want to guess how big arrays are. We want to keep track of that ourselves. Size of may be applied to variables. It is my recommendation that you do not do this, that you only apply it to types. And one of the reasons not to do this is that size of is computed when the code compiles. And we can change the size of array by assigning an integer pointer to different values. Like so. We can create an integer pointer, r, and we can manipulate it. So we can create a buffer or an array or a list or something else of size 10, compute the size of that value, store that value, change the size to 5, and then look up the size of array minus 1th element and trigger a segmentation fault because we are now pointing to a different memory location. Because we can change the value of variables, we have to make sure that whenever we are fiddling with memory, we are keeping track of what is going on in the memory. This is the thing that means LLMs will never be able to write this kind of code. They cannot process internal state. It would require a different form of technology. If they successfully do this, they're following code styles meant to prevent them from making mistakes, which is independently academically interesting, right?
And every pointer is effectively an array of one element? Like,
Yeah, that's a reasonable way to think of it. Yeah.
Oh.
Yeah, pointers and arrays of length 0 or 1, depending on how you want to say it, are identical. And in fact, I've used them interchangeably a few times in this class without mentioning it. The really big difference is at compile time. If you declare an integer star, it does not get any memory. And if you declare an integer array of size 1, it does get some memory. It gets some memory on the stack. But separately, you both get 8 bytes describing where that is. It just might be initialized or uninitialized. I really like using arrays of length 1 or 0, depending on how you describe it. Okay. So we can use a character star. I guess that should be escaped. No, I didn't want it to be escaped because it looked weird. We can use a character star in a function argument. This can account for arrays or strings. It makes no difference, right? A null terminated character array is simply, we just call that a string, right? But that is a social convention. And what does this mean? When we call a function on a character star, the information that we provide to that function is the location of some string. We are not providing the string. Why do we do this? Well, the function which we call must know how many bits or bytes it is supposed to read that correspond to the arguments. And a string can be of any length. So unless we write separate functions for strings of every length, or we restrict every string to be of the exact same length, which is possible, right? We could pad them up to 512 bytes or something, right? That's completely legal. You can implement your programming language that way. We did that with 496T, and it was very, very low performance, right? So you understand the costs of doing that, but it is possible. So what that means is that somewhere in the computer there is a string written. We do not send that string to the function. We send that string's address to the function. And then the function goes and looks up the bits of that address and acts accordingly. That's what's going on when we work with a character star. Now, often in practice what we have used is we have used the notion of declaring a character array of size n in some function, taking that value, the 8 bits that represent the location of that character array, and providing that to some other function. What that means is when the function which we call, so helper function, for example, it begins manipulating values in that array, it is looking at the same memory that exists in the main function. It is working on the same bits. None of this is necessarily duplicated. That is really weird and really hard to think about and really hard to debug. You can actually make these same types of mistakes in Python if you are bad enough at Python and you think of it as C like I do. So I semi-regularly have references proliferate throughout my code base and cause my code to explode. So just look out for that. When you are passing pointers around, you are not passing copies of data, which means that if you call a function on some string and you edit that string in the function, it is edited in the main function, right? That is very weird. These strings are not immutable. You see why Python has immutable strings. It is to prevent you from doing this mistake, right? And then it correspondingly leads Python to be slower, right? So let's have some takeaways. Pointers do not contain data, except they do. They contain locations. They tend to end in 0 because they tend to be multiples of 8 or 16 or larger values, right? They tend to be big blocks. We can always update the location of a pointer with single equals assignment, including to illegal values, right? We can set it to values that have no correspondence in the memory system. No one's stopping us from looking at things that we're not supposed to look at until we try to and the operating system kills us, right? But we can write code that is against the law. I think of them as the name, the address, the location, the description, something of this nature of some bits. I do not think of them as bits of independent interest, right? And these pointers are often used to describe arrays. They might be used to describe data structures. They are used, for example, to describe the multiple precision integer type. So that is what pointers do. Arrays are distinct, and they're distinct specifically in that we have to provide a defined size of the array. What this means is that even though an array is described by a pointer, that array has specific properties, that the memory is protected as long as the function that declared that array has not yet returned. As soon as it's returned, the memory goes away. This means that we are banned from using single equals assignment to change the values of arrays. Now we can set a pointer equal to the value of an array and then change that pointer around. That's fine. We can call a function on the value of the array, and then we can change the name of that array inside the function, right? But those are all just changing names. We cannot alter the one original definition of the array. That is against the law. Arrays do two things. They both provide you the number of bits required to store all of the values in the array, and then somewhere they also give you a variable that describes the location of the array. So you get two things every time you declare an array. That's weird. In fact, I would argue that's kind of spooky and probably should not have been allowed, but it is allowed, and it's kind of cool. Any array with any name can only describe that one specific array, and the solution to this problem is Malloc. Malloc stands for memory allocation. There exist calloc and ralloc, which are more modern implementations that I'm not going to teach you about, but if you start using them yourself, that's totally fine. Just look into them. Malloc is the solution to the problem of how can I write a program that calculates how many bits it needs and then asks for that many bits. We do not have the ability to do that yet. Right now, before we start running the program, before it even starts compiling, we have to decide how many bits we need for everything. And that's good. That forces us to think. And it's bad because it makes using data structures impossible, right? We have no way right now to deal with infinite size data except with streaming, right? And you know I love streaming, right? Let's see, streaming. Severance? Yeah, play to the crowd. I love Adam Scott because he was so funny in Parks and Recreation.
Yes, you love.
Watch good film. Okay. Like there's a whole world of cinematographers, and you're watching Americans.
Severance?
Owned by Steve Jobs' ghost.
That's unfortunate, but it's still
Yeah, okay. Yeah, I've heard it's great. I'm unfortunately incapable of experiencing art because I'm a STEM major. Okay, so here's Malloc. Going back and forth here, there's a lot of documentation on Malloc. I think I'm going to tell you what you need to know. Malloc is a function that does three things. And why am I holding up two? Because two of them are visible and one of them is a secret. We get a size. We say, dear operating system, give me this many bytes. That's a size t. Size t's describe numbers of bytes. They don't describe numbers of bits. Dear operating system, give me this many bytes. And the operating system says, sure, your bytes are ready for you. They are at location void star. Why is it a void star? Well, the operating system is not taking a position on what type of bytes you have. The operating system does not care about types. It does not know if those are going to be used to be storing characters or integers or floats or an image or a file. So it says, well, this is some kind of location of some kind of information, but I do not care which. Now, the operating system is doing one other secret thing here, and it's going to try and avoid telling you about this, but you're going to find out anyways, which is that it is making sure no one else messes with your bytes until you give it permission to mess with them. This is good and bad. What this means is that you can assume the integrity of any bytes which you malloc. It does not mean that you can assume someone else is going to take care of them when you're done with them. When I was a little kid and I went to play with my friends, which I had then, I did have friends when I was a little kid, at the end of the playing with the other little kid friend, you always had to put the toys away. Do you all recall this? This was a foundational part of my psyche for many years, right? One day, one of my little kid friends didn't help me put the toys away, and I have not had a friendship since then, right? So, the only person I trust now is the Linux kernel, because the Linux kernel always helps me put my toys away, right? So my only friend is the parasocial relationship I have with Linus Torvalds, right? And this could be you too. You can aspire to be just like me. No one can stop you. I often get feedback that you don't want to be like me. That just means you're learning. Okay, so this Malloc thing, which is just a void star, it can be anything. And an example of something it can be is it can be a length prefixed array of null terminated character pointers. So we can actually jam the entirety of argc and argv right into one of these beloved void stars here. Now, I do want to point out I was playing a little bit fast and loose there because the argument vector of C is an array of what? Of character pointers, which means those things are also addresses. And now you have discovered a naturally occurring recursive data structure. You're welcome. I love C. I want to yap at you a little bit about void stars. Void stars are cool. Probably my favorite type. I really believe in strong individual freedoms. I'm a libertarian. I love guns and gold. And if you love guns and gold, you'll love void stars because you can do whatever with them that you want, right? Just like guns and gold, you can do whatever with them that you want. You can donate them to the Oregon Humane Society. I don't know that they need guns or gold. You can trade them for cat food and then donate that to the Oregon Humane Society. Though I don't know, the cat food you get by trading for guns and gold might be pretty sketchy cat food, if I had to guess. So these bits can be used to do whatever you want. You are all powerful. There's no rules. This is the Wild West. A real place that actually exists. Okay, there's going to be a test, and you better pass this one. Okay, are you ready? Are you locked in? Listen carefully to what I'm saying. Can I get a whoop whoop for Manifest Destiny? Excellent. You're learning. Right. Good job. Okay. Anyways. Unlike the American Settler Colonial Project, which I didn't mean to bring up, but I have one brain cell, and it hates capitalism. The bits that you get back from Malloc are not stolen from anyone else. They were just out there existing on your hard drive. Now, it is true the hard drive is made with stolen mineral wealth, probably from Africa. But I did my best, okay? So, when you get these bits and bytes back, you should treat them right. And the way I treat bits and bytes right is I give them a name, and I give them a type, right? So when I get some bits and bytes back from Malloc, I cast it to whatever type it's supposed to be. I take that void star and I turn it into a character star. This is not required. The compiler will not freak out if you don't do this. You should do this because it's the right thing to do. Why is it the right thing to do? It documents your code. Why is this the wrong thing to do? Could this be an anti-pattern? Is this redundant? Yes, you are welcome to argue this is duplication. I specifically think it is more important to do this in the case when this variable has already been declared and it does not say on the same line what type it is. Right? So this is a way to document your code. And this form of code documentation will throw an error if you do something sketchy. So this is slightly better than a comment, right? My recommendation is that all of your mallocs should include a multiplication by a size of. That way, just in case Unicode standard shows up and turns all of your characters into being 16 bits, which they've been trying to do for decades, right? Your code doesn't instantly explode. And that's that. You can tell this is from a previous term because I have a space in between the end of the line and the semicolon. Everyone hated that last term. I tried to take them all out, but I actually still think it looks better. Okay. We get a void star back from Malloc, we turn it into something else. What are we turning it into? Well, we've turned it into 6 characters worth of stuff, and we've called it a character star, and we've put it in pointer, which means that I can now store hello, which is 5 characters long, which means it's a string of length 6 because it has the null terminator, so I can now put hello in this thing, right? It looks a lot like an array, but I get to decide how big it is by manipulating this, which means I can put I there, I can put a variable there, I can calculate something. So, oh look, it's hello, just as predicted. This is virtually identical to a buffer. We create a buffer of size 6. What is a buffer? Same thing as a vector, same thing as an array. It is n bytes consecutive order. And the only thing that is special about these bytes is when we interact with them, we understand, we have a sort of handshake agreement with the compiler that they hold characters. We do the same thing here. This is the same operation. We're also getting 6 characters. We're just getting them through malloc. Then we have a size ti, which is what we should use to index through these things, right? So then we just loop over. We take string I, which is right here, and we set the buffer value and the pointer value to be equal to that. I just print out all 3 of them, and it says hello, hello, hello. You know how you're supposed to say hello multiple times for emphasis? I do that. My voice is fading. Am I yelling? Am I hyped up? I do love Malloc. Do you all love Malloc? Yeah. I was listening to Amity Affliction on the way down here, and I'm so sad. Okay. All right. We are vaguely aware of size t, because we've seen the sizes of things before. We are vaguely aware of void star, because I introduced it right now. I would like to impress upon you that these two things have to be the same size. Why is that? Well, the size t describes the size of anything that can be in memory, which means its minimum size is 0 and its maximum size is the size of your memory. A void star describes the location of anything in memory, which means its minimum location is 0 and its maximum location is the size of your memory. They have the same minimum and the maximum. They are both linear. And so if we have an intersection at 2 points of 2 lines, that means they're the same line. These things have to be the same size. I'm not going to construct a bijection between them. I'm going to give you this argument. It is correct. You can check it. Now, I am not going to claim, because I've done this in the past, that every single implementation successfully makes sure void stars and size t's are the same. There is absolutely some compiler or some operating system or some piece of hardware out there that does not do this, and I don't know why. There's a bunch of 48 bits memory spaces floating around, and I'm a little bit nervous that someone implemented a size t as an int 48t in one of those. That seems really weird to me, but it's definitely allowed, and those void stars are definitely still going to be 64 bits because you're running a 64-bit OS on that 48-bit memory, right? So do look out for that, but you can trust me, this has never been wrong. Okay, here's a void star. If you become an embedded systems programmer and make the ungodly amount of money that embedded system programmers make, I encourage you to run something like this with or without asserts. You could also just return this value, right? And then you would get essentially the assert back at the command line. How's Vim work? Let's see. We do what? That's what I had in my buffer? Okay. How do you copy? What? No. Control Shift E? Yeah, I don't know what I'm doing. I've completely bamboozled myself. Also, this is a new device. It has different settings on it. Okay. I tried that. Wait, size T is undeclared? Ugh. Exhausting. I'm emotionally exhausted right now. How do I mute? Ah! Oh, I just sent an mute command to Vim, and this is how it interpreted it. I did not hear or was able to think about that. Sorry.
These executed.
There's nothing preventing them from being executed, but they're not denoted as execution. So here's an example. I compile something into a.out. I fopen a.out, and I copy the contents of a.out into a void star. If somehow I could bamboozle my executable into jumping into the beginning of that, it would start executing it as an executable, right? Depending on your version of GCC, and one of the reasons I don't check this all the time is like every time I find a way through GCC, it gets patched pretty quickly, right? Generally speaking, compilers want to prevent you from writing self-modifying code or code that can execute itself, but obviously you can include a string in a C file and like that string can be an executable or something else, right? And it's good that's allowed, right? We wouldn't want there to be some restrictions preventing us from doing that. What am I doing? This is read only? Standard def, right? Oh, help text. Oh yeah, it says row. No. Okay. Hold on. I have a plan. Okay. Look. Those things aren't the same for some reason. Probably that's because I didn't specify the return value. Let's see. Then I kind of want to return a size t. Okay. Cool. They're the same. Ta-da! Okay, and I have to hold down function and then hit F11 to full screen this. Okay. My new computer seems like really fast, but all the keyboard shortcuts that I use are different because there's a function key on this one and there wasn't on my old one. There's also a little key with the Colab logo on it that I'm trying really hard not to press because I don't know what's going to happen if I press it. But I'm worried I'm going to accidentally donate my laptop to Cortana. A actual existing product named after a character from Halo. Way to go, Microsoft. Okay, so I know what you're thinking. You're thinking, I wish I were somewhere else, and also, what is the stack? Okay, and so I'm going to tell you about what the stack is, because I can't actually teleport you anywhere else. So you are probably all familiar with the stack from Burger King, which has a sandwich called the Stacker, right? And I love stackers, even though I'm vegan, which has been really hard on me. Stacks are inspired and did inspire the data structure of the same name, which is actually an abstract data type, but in this case, it's also a data structure, right? And then there's also a heap. Okay, so far in this class, some of you went out and started using Malloc without my permission. And I don't really agree with that. I sort of gave an entire anti-patterns lecture on why you shouldn't have done that. And then I tried to generate a prime number and was like, wow, I wish I had Malloc, right? So maybe you're right, maybe I'm wrong. Someone's right and someone's wrong. Anyways, so far we've only used the stack. And what does the stack mean? It's a linear sequence of bits, right? Every time we ask for a new variable, it just goes right after the next one. We get however many bits we asked for based on the size of the variable. We ask for an array, we get a multiple of that size. That's all. Very straightforward. All the bits are in one place. We call that the stack because things stack up just like the stackers at Burger King. Hashtag not sponsored. Wait, can any of you get me sponsored by Burger King? Presumably there's like a data scientist in here that like did a project for Burger King and like knows someone. That's right, they stopped coming to class. Right. Okay. They're still enrolled. They're on the roster. I'm sure there's at least one data scientist in here. Okay. There's also this thing called the heap. Did you all learn about heaps in data structures? Okay. A heap is like it's like a binary tree. Did you learn about binary trees? Okay. Just imagine a binary tree. It's not really a binary tree, but it's like kind of like that, right? Okay. But it's a nonlinear. It's a nonlinear structure, right? Hash tables are fine. Oh, do you all know hash tables?
Like a dictionary?
Sure. Yes, dictionaries. Well, we'll call the heap a dictionary. That's really stretching, but that's fine. Okay. The stack and heap exist in different physical regions of system memory. These physical regions correspond to transistors. In other versions of this class, and I've decided to not mention this on the slides, a lot of people like to talk about the difference between virtual and physical memory. I don't. I think it's fake news, so I'm just going to tell you they're all in physical memory. Now, the numbers don't necessarily correspond linearly across the stack and the heap, but within the stack and the heap, they are linear relations. So stack memory is near stack memory, but distant from heap memory. And we can measure that by running this following snippet. I created 3 arrays, each of size 256 characters. And then I created 3 pointers, each of size 256, which is 256 pointers. I deviated from my style of including size up here because it didn't fit on the screen. So, okay, I'm the worst, right? And then I printed out all of their locations. And what do we note? Things on the stack have very, very large values. They start with 7FF. Those are really big numbers, right? Things on the heap start with 556. Now, that's still a big number, but it is a considerably smaller number. The next thing you should be thinking about is you should be thinking, wait a minute, this is probably running on a 64-bit system. 64 bits should be represented... Wait, did I say 64-bit system? Right? Okay, so if I have 64 bits, and each hex character represents 4 bits, then 64 divided by 4 is 16, which means there should be exactly 16 characters here. And I should count them to make sure there's not a bunch of preceding zeros here, right? So there's 4. There's 4. Oh, that is only 12 characters. What does that mean? Just a few moments ago, I told you you might be working on a system with a 48-bit memory space. You are. It is very unlikely you're working in a 64-bit memory space. These things are 48 bits long. They're just existing in something of size 64 bits. They have a ton of preceding zeros. So however close or distance these are to each other, they are a fraction, and a very tiny fraction, of the space addressable with 64 bits, right? These all end in 0. What does that mean? This is hexadecimal. If you end in 0, it means you're a multiple of 16. That means that I am working with a multiples of 16, which means I have essentially a 64-bit word size. All of these are lining up on the boundaries, right? Another thing that's going on, that says 0, 1, 2. That is what? The 16s, no, that's the 1's digits, the 16 digit, and that is the 256th digit. I asked for 256 bits, I got them. These things are exactly adjacent to each other. There are 0 bits between each of these things of 256. What that means is if I look up the 512th location of array 0, I will get the 0th location of array 2. That is weird. You have to be ready for that. If I look up the 512th entry of array 0, I will get the 0th location of array 2. Because this value is 512 more than that value. The same thing is true on the heap. I was quite surprised to see this, and I believe this is because I compiled with C89 flags on. I've taught systems programming a few times, and especially when you teach security, you do the most modern, right? I have run this code before and gotten this pattern here, A, B, C. Notice this? So, if I look up the 512th location of this array, pointer 0, I think I get the length minus 8th of this array, but there's some dead bits between here because we see A, B, and C increases. So there is 1 word between each of the heap allocated memory locations. And probably those are there so that if you read off the end of array, there's probably something there that is called a canary bit, which is a value that is hard to guess and write randomly. And the operating system reads it from time to time to make sure it's there. And so if it gets overwritten, that's evidence of memory tampering. You're doing something you weren't supposed to do, or at least something you didn't say you were going to do, or say you intended to do. And so if that memory is tampered with, then either the compiler or the operating system will blow up your code. I don't know exactly how that works. It seemed very complicated. I tried to learn how it worked once and I gave up. Oh yeah, it is much more likely this happens because all the malloc calls are right next to each other. But there's no guarantee. And there's no reason to assume that either. That said, many like security attacks rely on guessing this will happen. It happens at very high probability. You should just always check if you're curious. Okay. We've only used stack memory so far. Bits live on the stack. I think of the heap as a scratchpad space, where there are no guarantees of where the bits land. As Andy pointed out, they might be next to each other, they might not. The way that it is decided whether they are close to each other or not is using magic. A wizard did it. And if you want to get a sense for how that happens, you should screw around with Malloc for thousands of hours, as I have. It is a great joy. Malloc and running are my two things I do for fun. Specifically, I run Mallocs. And Malloc also runs me. Okay, so let's look at the difference between the stack and the heap. Okay, on the stack, we put things of fixed size. On the heap, we put things of arbitrary size. We allocate things on the stack by declaring variables. We allocate things on the heap with Malloc. The stack is managed by GCC, and the heap is managed by a wizard named the operating system. And the stack tends to have higher values closer to FF, and the heap tends to have lower values closer to OO. I'm going to present some slides that are shamelessly stolen from people that actually understand this, who had undergraduate degrees at UIUC, and understood this better than I did after I got my PhD while they were teaching it to other undergrads in their second and third year. They now work at Apple, and probably Ray Hao Gao has graduated from Georgia Institute of Technology by now, but I couldn't find any evidence that that was true. So these are who I want to be when I grow up. Let's look at the stack. This is the memory layout. I actually found this on someone's blog. I wonder if it's linked. No. I'm gonna like walk over here and point. I'm not recording today. Wait, no, am I? Yeah, I am. The webcam's not plugged in, but I have a new computer that doesn't need the webcam. If you're looking for something to do, go on YouTube and see if the recording's working. Okay. Like, watch Jenny Nichols. We love Jenny Nichols. That's funny. Are there any YouTubers we love as much? I think so. I like ideas. Okay. So we can imagine that one of our executables has a memory space. You'll note that this is labeled virtual memory space. What did I tell you about virtual memory? Don't think about it. It's fake news. Yeah. Wait, what? Yes. I'm not currently live on YouTube. That's interesting. Where am I live?
It says there that
Wait, I'm unlisted, I bet.
oh,
That's fine. Whoa! Oh, and I'm probably in the wrong playlist. Thank you, Olivia. Do I have like a Linkerino? Where do I? How do I share? How do I like, comment, subscribe? Wait. Okay. Copy. Is this a private window? Yes, okay. All right, and we close that before it pops up and I get banned. Okay. Thank you. It was unlisted. Why was it unlisted? Because I was doing a test earlier to make sure it worked, and I unlisted it because I didn't want you all to start throwing your cash money at YouTube Premium to watch me. I worry about you all. Okay. Mostly think about the stack and the heap. If this were a compilers or operating systems class, we would talk about a little bit more of this stuff, what's going on here. This is essentially the code. It is compiled. This is the libraries that are read before the code starts running. Initialized to 0 at program start. I don't know what BSS stands for. It's probably one of the other things. We understand there's a lot of bits floating around in our computer that constitute an executable. That's all this nonsense. I don't care about that. You're not supposed to mess with that stuff. Now, you can go and figure out how to mess with it if you want, really. By all means, right? I have never found it academically interesting, that stuff. So we mostly work with the heap and the stack. The heap builds up, and the stack builds down from the top. Mm-hmm. And they might grow to meet them someday that hold tight to the ceiling.
But like the stack, it's
Stack has a fixed size at runtime. The stack has a predictable but arbitrary size at runtime. The compiler knows how big it will get per function call, but does not predict the number of function calls. You can make the stack hit a limit by writing a recursive function that has many variables. Historically, it was when the stack hit the heap. Now in virtual memory spaces, you just exceed some OS-defined limit. We can do it right now. Or sorry, what was that? Why do you need to know? That's not a... Historically, it was a convenience. It is no longer enforced by modern versions of C. It is possible to infer sizes. It was easier to write a compiler when you didn't have to do that. Yeah. So at least C11 has variable length arrays, VLAs, and those are totally fine. The compiler can handle them now. In earlier, less stable combinations of hardware and compilers, it was not possible, but it was not possible for a technical reason, not a theoretical reason. It is deeply unsafe to not do that, right? Let's blow up the stack. Gonna recurse. None of these need types. Should they have types? We'll pass some ints around. Something I always like to do when I'm trying to cause problems, or I use a lot of memory. That's probably fine. I'm gonna do with x. I'm gonna say if x recurse x minus 1. Ooh, I wonder if int's big enough. I bet it is. We can just return this, right? So this is a way to count how big x is. This is going to return what number x is, right? This is the identity function implemented recursively. Int main recurse. That seems fine. Ooh, it thought about it for a while. Okay, so right, there's nothing against the law in this code. That's all completely allowed, right? But what happened is I ran out of space and caused a segmentation fault at some point. And I think we can we should verify that it's allowed by putting a reasonable size number here. That's fine, right? And so obviously what we really want to do int arg how do I turn is it let's see, what am I trying to do? A toy. Does that give me the number that I type at the command line? I think it does. Do I need string? Ooh, I'm recommended. I'm gonna see if I need it. Ah! Do you all know Vim yet? Is it just me? That seems bad. Oh, I didn't provide an argument. That's fine. Okay. Wait, no, what am I doing? I don't care about the warnings. That's better. Let's do some binary search. Oh, is it? Oh, it's not 250. Okay. So, my stack is allowed to be exactly because there's in argc and argv, right? So that's why I'm getting slightly less than 255. So that is 2 to the 8th. That is 2 to the 14th. 2 to the 12th. So I'm allowed to use exactly 2 to the 20th bytes before the operating system pulls the plug, it looks like. No, because these are longs, so it's 4 times bigger than that. Or 8. If my brain were fully functional right now, which it's absolutely cooked, I don't know why, I would be able to figure out how many bits you're allowed to use before the operating system turns you off. But this being so close to a power of 2 is extremely suspicious, right? So the actual thing that is controlling the size of the stack is what happens on your hardware. At some point, it will stop working, right? Let's step through an example. Okay. When I run this following code, int a, what does that do? That stack allocates an integer. The integer is of size 4 on my system. We don't assume its size. We make no claims about its size. And it allocates it with no value. This just reserves space on the stack. That's what I say here. When we get to B, we do the same thing. We go to the next lower location in the stack. We name that thing B. B is not written down anywhere. It is only known to the compiler. While the code is running, there is no notion that this is B or not. It is simply a number in a location. And we populate a -3 there. On modern compilers, these question marks are probably zeros, but you should not assume that. I'm not ever sure how to denote that it's the integer value -3, so I'm using an int cast on the number, right? And notice those are signed, so I'm allowed to put negatives there. This stack belongs to the function main. We can also put 1, 2, 3, 4, 5 in there. That is also C. The exact same operation is taking place. This is all totally fine and reasonable. This is the stack owned by main. Okay? Now, when we get here, we are going to change control flow. The control is going to divert into the hello function. The hello function is going to ask for 4 bytes on the stack, which it is going to call A. Notice these things are both called A. That is totally fine. I'm denoting this as hello.a and main.a. This A is equal to 100, and it is going to live on the stack in the first available stack location after all of the values in main. Now, when we were doing, for example, 496T, we could put really, really big numbers in here, right? 4096T byte-sized numbers, and then we could refer back to them from inside hello. That's the same thing that's going on here, right? Hello is called with no arguments, so we don't see that here. Okay. Now, wait, what did I do? Oh, I pressed the wrong arrow, right? Okay. Okay, so I'm going to flip back and forth between these things. What's going on here? Essentially just a renaming. Okay, so A is 100. We throw it on the stack. Then we're going to do a return call. What is the return call going to do? Well, the return call is going to take the value of A and put it on the stack. But where is it going to put it on the stack? Well, first of all, it's going to free all of the memory associated with hello, which means that it's going to get rid of the current A. So it's going to take the 100 off the stack and put it back on. And it's going to change from being named A to being named the return value. But the 100 stays in the same place. Now, once that return is called, control diverts from inside the hello function back to the main function because the hello function has returned. It is no longer active. And within that function, the integer d is going to be assigned to the return value. The return value is the same 100 that we've been passing around back and forth between all of us. There's the joke that, like, all Zoomers or trans people or name your oppressed population pass around the same $20 over and over again. That's what we're doing with this 100, right? But we have $100 because we're computer scientists, right? Okay, so we're passing this 100 around. The 100 gets passed back to main. Main instantly names it D, but it stays in the same place. It actually exists in transistors somewhere. Nothing's actually going on here under the hood. The compiler is creating the illusion of that for us, but that D is just changing names, right? The 100 never moves. That's why we use a stack. This is efficient. Now, if you write modern code in GCC, it does a bunch of stack and heap nonsense at the beginning of every program. I don't know why. I've looked at what it does. I hate it. I have no idea why it works. So I don't think this actually happens with modern GCC, but it probably happened with, like, 1969 Bell Labs CC before GCC came in. Anyways, the end-to-end, this is how I perceive what happens. We push main.a with no value. We push main.b with 3. I lost a negative sign there, that's fine. We push main.c, 1, 2, 3, 4, 5. We call hello. And it pushes hello.a equals 100 in returns. And then that becomes main.d. That's it. That's how the stack works. Do you understand the stack perfectly? Say yes.
Nope.
Okay.
How do you, I know, like, in stacks when we learned it in data structures, we were only able to access stuff from the top. Are you able to access anything in the stack at a time? Okay.
Yeah, you're able to access anything you have the name of or can calculate the location of.
Okay.
So there's two different ways to get there.
On, like the stack abstract data structure.
We have, as a rule, you're not supposed to overwrite other things, but the single equals variable assignment is the way to write. In terms of, like, versus the stack data structure, the real thing you're not supposed to do is you're not supposed to allocate memory down here. So the memory is behaving stack. The values stored in memory are not behaving stack. I think I saw another hand. Yes.
So, like, if you have, like, sub, like, are you still doing the same thing with A D? What's other? Yeah, but, like, is Substack or, like, just somewhere else?
Sorry, I missed the word you said after sub. Substack. Okay, so functions have their own stack, but the stack just goes on the end of the current stack. If you fork, is that what you asked? Are you asking about?
One, it has, like,
Right, different threads. There's the difference between processes and threads, and one of them copies the stack and one of them uses the same stack. And I don't remember which one. And I think also the heap is shared across threads, but I tried to share a heap across threads recently, and I think I couldn't translate between it because they had a different virtual address space. So they could see the same information, but it had different addresses. So the heap is very weird. The way to tell what the stack does, which I never remember, is I just check every time. So if I branch and create 2 processes or 2 threads or 2 of anything else, I just see if I can refer to earlier values. And sometimes they're there and sometimes they're not. There's probably, like, a reason for all that stuff. It felt totally arbitrary to me every time I've learned it.
If you made another variable right before that, and there was something, what would happen to the A when you return? Because it would be in the same place, right?
Yes, it is coincidental in this example that the A stays in the same place. What actually happens is we erase all of the stack from the function and then place the return value. That return value is not stored on the stack while that operation is taking place. It's being stored in a register, which is the sort of the compute area. So really, we're wiping all of that information, computing the result of an expression. That expression happens to be the identity operation on A. Then we're placing the value of that expression on the stack. You can sort of make this arbitrarily complicated, and higher levels of complexity make different things easier to explain. But you can imagine I could put A plus A here, right? And I would calculate 200 and then push that onto the stack. Okay. Other questions? Stacks are fun. I guess you can see this in a debugger. I just print memory, always. You can just start printing things. Knowing, especially, remember, like, months ago now, we wrote print B, and you just print the binary values of things. Just print everything. Like, it's not that hard to find. When I get really messed up when I'm writing code, I put a little print statement at the beginning of every function that prints the memory address of the first declared variable, which tells me where the functions are on the stack, and then I can build the stack frame manually. Don't tell Professor Lucas Cordova I do that. He likes debuggers. I've never turned one on. I don't even think I have GDB installed. Hell yeah. Okay. Just write code without bugs in it. I don't know. We're not going to discuss stacks. Okay, so there's 50 slides left in 18 minutes. Is this stuff important?
Yeah, lock it.
Yeah, I think I'm going to lock in. Okay, all right. Here's a heap example. Wow, I love these screens. That looks so small on my screen. You can actually see it up here. Okay, so the stack and heap, we think of them as being in different conceptual locations. We also see most of the heap as being crossed out but existing. That's because at any given time when we call malloc, we don't know which bin of heap we're going to get passed to us, right? Okay, so over here, I say int star p equals malloc size of int. I am not int casting the return value of malloc because I wanted to fit in one line. Is this easier if I make it big? Do we like this better? Better? Okay, very good. Okay, so what's going on here? We declare a variable, which means the variable is allocated on the stack and it is of size integer star, which means this is 8 bytes. We malloc size of int, which means this over here, we have some integer that exists somewhere on the heap. We do not care where on the heap. The only way we know where it is on the heap is we have its address. Its address is 8 bytes in length. And this is of size integer, and it does not contain any value. Okay. We can throw a 0 in there. That doesn't really affect anything. That's not too exciting. Okay, let's pop this one open. Okay. Here's a second malloc call. The second malloc call corresponds to a queue being pushed onto the stack. This queue is also of size 8 bytes. It is the same integer star size as p. We think of these as having arrows. Really, this is the correspondence between a numerical description of a memory location and the actual memory location. We ask for 2 times the size of integer. We can think of that in a few different ways. The way I'm going to think of it as is we have 2 adjacent integers with no particular value in them. There's just whatever bits were already there in memory when the operating system tossed these bits to us. Really, we own the location. We don't own the numerical values, right? Okay. We throw a 1 in the first location, or I should say 0th location. Sorry. We throw a 1 directly at the location described by q. We use star q, which refers to the location, or the value at the location of q, okay? We throw a 2 in the second location. I'm going to make this one big again so we can see it. There we go. We have a 0, a 1, and a 2. This is assigned with star q, which is equivalent to q0. And then we have q1, which is 1 more than q, which is this location. Now, what we can do in this next line here is something that is against the law. This is banned. We set p equal to q. What does this do? Well, p is an integer pointer. We can set it to whatever value we like. I can set it to 0. I can set it to -1. I can set it to the value of q. What this means is as soon as I set p equal to q, the numerical value in q, which is equivalent to the arrow to this location, is stored inside p. This means that this integer 0 is stranded. It must exist there forever, or the operating system is violating the rules. Why are you cheering for that? It escaped, it got out. This 0 is the only one of us to make it. Anyways, this is bad. Don't do it. Let me tell you how not to do it. We're going to free it. Okay. So, that's the same thing I had. Blah, blah, blah. P holds the address of the 0. Q holds the address of 1, 2. This is free. Free is the word that comes after malloc. Notice that there's a bunch of these together. Free accepts this, like, I hate this type. That is a void star underscore capital N nullable. That is, like, the least human comprehensible phrase in all of existence. What does that mean? Pointers can be freed, but not all of them. How do you tell if they're freed? They can be freed if they're on the heap. They cannot be freed if they're on the stack. How do you tell if you're on the stack or the heap? That's the trick. You don't. You have to know. Now, fortunately, you are the ones writing your code, so you can just check and be like, star R This is named after Colin Starr, right? Star R, right? Okay. Any Colin Starr appreciators in the chat? We love number theory, don't we, folks? This is a Malloc. This is a buff. If we set pointer equal to buff, we cannot free that. And if we set it equal to R, we can free that. Is that confusing? You bet. Use Java. Okay, every Malloc in your code should have a corresponding free, otherwise you run out of memory. I was looking at some code the other day that had a ton of memory leaks in it, and it worked just fine. So now I'm wondering if I've been lied to my entire life. Okay. These things are both nullable. Why are they both nullable? The return values of Malloc. The return value of Malloc is nullable. Otherwise, it's not. That's the rules. Okay. We can put the same star nullable into both P and Q. That's bad. Do not torture your poor OS. Someone I have a parasocial relationship with had to write that, right? So I will personally be offended. Some of you may have heard of the languages Java and Python. They have a garbage collector. I prefer the term sanitation engineer, which hasn't really caught on. But anyways, there's just a little component of the executable that's running. You may have noticed Java and Python are both executables, and GCC just creates executables. There's a reason for that. And that's because in GCC, you are the garbage collector. You got to take out the trash, right? Who loves taking out the trash? I took out the trash last night. I was out of trash bags, so it was much harder than I expected. I was like, okay. If you try really hard, you can write a memory leak in Python. I leave that as an exercise to the most deranged student in here. Okay. You have to write something with recursive references and then delete both of them at the same time. Okay. Here's what you're supposed to do. I have added a free call. What does this do? Can I hear it for freedom? Yeah, I wasn't sure either. I do like, I think California has a registered state party called the Peace and Freedom Party. Yeah, right. Yeah, I think they're communists.
That's not right.
Peace and freedom?
Rhetorically, peace and freedom tend to mean like, you know, patriotism.
Sorry, I gotta look this up. Peace and Freedom Party. I'm convinced they're communists. Left wing! Left wing! Wait, they're from New York? Oh, that's kind of... Oh, they hate the Vietnam War. Oh, also, like, in 1966, I don't know that freedom was right-wing coded yet, right? Yeah. Hell yeah, Claudia de la Cruz. This is who I voted for, and all of my family was mad at me for not voting for a Democrat. It's me. I'm the reason for fascism. Okay, so here's free. Oh, that 0 is still there on the stack. It's there on the stack, but you don't know how long it's there for. It's there until it finds something better to do. If you want to figure out what is happening with memory in your program, use Valgrind. I think someone started working on list and we don't want to say who it was. But I was maybe going to add a note to list that I'm going to run your code through Valgrind and see if it works. Huh? My what leaks memory? Yeah, the tester leaks memory. Oh, okay. Well, okay, I don't know. Anyways, okay, let's make a memory leaking program. Wait, do I have Valgrind? My password is password, by the way. What? Really? Okay, it's not. It's something else. It's my other 8-digit password that is only alphabetical characters. Okay. So what is this? This is a memory leak. Bad. What do we do with this? We run it in Valgrind. You GCC it. You geck it, right? And then you Valgrind it. And you just prefix the executable name with Valgrind, and then Valgrind runs the executable, but does like a bunch of nonsense. Like, people love Valgrind. It seems like really good. And what's it do? It says, ooh, you lost. You're forced to hold this L, right? And so that's bad. This is the bad part. This is what's good. You're not supposed to lose anything. I can tell you don't believe me. Okay, so we'll Valgrind. Wait, what's the current A dot out? Is it this thing? It's the memory leaker, right? I have no idea what the last thing I ran is. Let's Valgrind it. Yeah, so this is what a seg fault looks like. Look at this. Look, it knows what I'm doing. It knows I'm a Toyin. It knows I'm Sturtolin. That's string token long, probably. Yeah, probably. What should we put in there? Let's throw 50 in there. Oh, look. No Malloc, so it's totally fine. All heap blocks were freed. Shout out me. Okay, let's assert something. I don't know. Oh, right, I couldn't figure out how to copy this, right? Double quote, wait. What? That's what I saved? The new OS is capturing a ton of my inputs, and I don't know what they're doing. Why do I keep going into visual? I keep typing V? I don't... Something's going on. I don't know what it is. Okay. What's going on? Wait, is this... Oh, no, this is the one with free in it. Okay, hold on. Vim bad. Okay. Gotta geck it. Too many gecks. Too many gecks. It takes some gecks to lose a block. Okay. Yes. Which half did I lose? I lost this, I lost this half, right? And then I kept this half. Good enough. Okay. Here's a demo of what happens if you free things and try to read from them. And this is the memory adjacent to techniques if time. Is any of this stuff cool? Not really. Oh, too many gecks. This is probably the best slide. Okay. If you add strings together, GCC stops you. Yep, that's cool. You can add things together and do an addition. What is this? Okay. If you add a number to a heap pointer, the amount by which that heap pointer changes is a function of the number times the size of the type. I thought I was in command mode. Okay. Okay, let's print something. Oh, I need to include standard IO. Why did I capitalize the S? Okay. So we can print percent D. I think it's a long. We'll do a long decimal. +1 equals percent LD, new line. We're going to print Q. We're going to print Q +1. Is this going to do what I want? No, stop. Ah! Who is pressing shift on my keyboard? I'm so boomer pilled. Okay. So, an astute student will notice that 56 plus 1 is not 60. Or is it because the next integer is at that location, because the integers are of size 4? Not to worry, I have a plan. This is a fun way to figure out what the size of long is. Wait, yeah, ow! I've got to stop making sounds. You'd think that, but like, I've overcome worse. Real? Oh, yeah, don't do this. See, that's why you should always include that there, so you can tell that your code's wrong. Anyways, these are 8 apart, right? Let's do one more. Does that undo? What am I doing? What was I gonna... Does anyone know what I'm doing? That's a trick question. Yes, you do. I'm doing pointer arithmetic. Come on. Okay. So this is a character. Characters are size 1. That's a capital X. That's lowercase x. Okay. Now, these are 1 apart. Why are they 1 apart? They're 1 apart because characters are of size 1. So when I add 1 additional character to this. So, this is cool. Look out for adding things to pointers, basically. Now, if you tell the compiler it's not a pointer, so if you cast it to a long and back and forth, it'll behave normally. But just be aware of that. It's very sketchy. These things are just doing pointer arithmetic under the hood, when you can verify that by running this code, where we add 1 to the star, or we use the brackets. So star, paren, r plus 1, close paren, is 100, and r bracket 1, close bracket, is also 100. That's just a loose tick mark. So you can navigate all of those things as you see fit. The brackets behave exactly as you would expect in Python. We can use unary and to pass the locations of things. You may have seen this a few times. You shouldn't need to fiddle around with this at all this term. I'm just providing it to you as additional information. And if you really want to, you should check your mallocs to make sure they successfully return memory. You can ask for more memory than the operating system will give you, or you can ask the operating system for memory while it's busy, and then it will also fail. So mallocs are returned on a best effort basis. They are not guaranteed. 1 plus 1 is always 2. Malloc is not always anything. And with that, I will see you next week. Implement some lists, maybe play around with Valgrind. Have a good time. I don't know what kids are into these days. Night Rain came out. Night Rain. Yeah. Yeah.
This research, or like, I'm working with the school, and we're doing like, we're supposed to like help him, and I realized it didn't really align with what I wanted to do with my summer. And